So module 6.2, energy changes. So what is energy? Energy is the ability to do work. We have, for instance, if we look at this waterfall over here, we have potential energy at the top, where it was, as the name suggests, ready to do something. And we have kinetic energy here where the water is falling, movement. And one way to measure this energy is force times distance. So temperature is the measure of the average kinetic energy, the movement of atoms or molecules in a substance. If these molecules move faster, it's a higher temperature. And we also have this idea of heat, whereas the energy that flows from hot to cold. So if we have a stove, we put our hand on the hot burning stove, the heat will transfer from the stove to our hand, never from our hand to the stove, always from hot to cold. The unit we use for energy, one unit we use is joules, an SI unit, which is the International System of Units, or Système International d'Unité in French. And just like the SI unit for temperature is Kelvin, for length is meters. So we have a unit for energy of joules. Something maybe you're more familiar with is calories. And we can convert 1 calorie to joule, which is 1 calorie here is equal to 4.184 joule. And you've seen calorie here on food products. They define calories the amount to increase, or the heat required to raise the temperature of 1 gram of water by 1 degrees Celsius. So we have the units of 1 kilocalorie, which is 1,000 calories. We also have 1 kilojoule is equal to 1,000 joules. And we say 1,000 calories is equal to 1, I say capital C cal as well. And how do we measure calories, what we see on the food? Well, one way is using this calorimeter. And the equation that we'll talk about is energy, or you can say Q for heat, or Q in our terms, is the mass times the specific heat times the change in temperature. This means change in temperature. So what are we doing? We put a piece of food in here. So let's say a candy. It has a specific heat, which we have to give you in a table. We can measure its mass, and then we essentially light it up. We ignite it, and it will give off a reaction. It'll heat up the water that's around it. So it'll heat up the water that's around it, which we can measure, and that will give us this temperature change. So if we know the mass of our candy, we know its specific heat, we know the temperature change once we light it up, before and after of the water, we can calculate its energy, and in essence, its calories. I mentioned the words exothermic reaction and endothermic reaction. Exothermic reaction is when you release energy. Endothermic is the opposite. But in this case, we have the combustion of methane gas. Remember, combustion requires review, just some oxygen to produce CO2 and water. But what happens? So in that reaction of C4H4 plus O2 gives us CO2 plus H2O. It's not balanced, but this releases 802.3 kilojoules per mole of energy. And what happens is we have the energy of the reactants at a certain level. This would be energy in the y-axis. And it releases energy to the surrounding, to everything around, so the energy of the products will be less for an exothermic reaction. Conversely, we have an endothermic reaction that absorbs energy, as we talked about photosynthesis. As an example, if you melt an ice cube, that requires energy from the surrounding towards the ice cube to turn into water. So in this case, for our ice cube, the heat goes into the ice and goes into the ice and melts the ice. So energy is absorbed for a endothermic reaction, and the energy of the products will be greater than that of the reactants. And conversely, the opposite, as we've talked about in the previous slide, exothermic reaction, that's a release of energy. So for instance, if you're making ice, this time going from water to ice as an example, we'll have our energy of the products being less than the energy of the reactants. And again, exothermic means energy is released. We also, in this process, we have the making of bonds, so the formation of bonds. We also have the breaking of bonds, and the bond energy is the amount of energy needed to break some of these bonds. And breaking bonds is always an endothermic process. So I just want to take this time to show so this is the combustion of propane. So if I drew propane here, which is 3 carbons, and remember each carbon should have 4 bonds, so I'm just drawing these H's around it. And this is water. Remember our Lewis structure for water. And our products. Why am I drawing 3? Because there's 3 of them. I should have drawn 5 oxygens as well. And we have 4 waters. So just to be complete, I'll draw the other oxygens as well. So what this is telling us, to break these bonds, again, the 416, let's focus on the propane. It requires 416 kilojoules to break a bond, but there's 8 of them here, you can see. So breaking of bonds, usually the reactants, we have to break the O2 bond, 5 of them, and we form these 6 CO bonds for CO2. We form these 6 CO bonds, and that is 4,818. We also form 8 OH bonds, hence the 8 OH here. And the calculation is adding these up with the energy required to break bonds. So it requires 6,530 kilojoules to break the bond, and to form the bond, 4,818 plus 3,736. When you do this math, which is the reactants minus the products, you get an overall change of an exothermic reaction of minus 2024. So this is just an example of using bond energies to calculate the overall change, to break bonds and to form bonds, to break bonds in a reactant and form bonds in a product. That's how I wanted to touch base on energy.